Welcome back, everybody. So this is a question that I feel like maybe we're able to do based on some stuff that we've already done. But if you try to work on this, try to answer, say, maybe this question is the easiest first. But this is going to be a motivation for understanding normally distributed random variables, which is what we are doing today. So see if you can answer this question, and then we'll do it together and move forward. And in the meantime, I'm going to give you back your quizzes, which you're going to give me. Sorry. Leanne. Oh, no, Jennifer. Where's Leanne? William. Yep. You prefer Mary Beth, right? Not just me. So was anybody expecting one back but didn't get one back? So I'm going to post solutions to this quiz soon. Not many people did very well on it, but I think we went over at least one of those questions. So hopefully, you know. All right. Does anybody have any big news that they want to talk about before we do this? Anything fantastic happen over spring break? Good. We don't have time for it anyway. Let's go for it. All right. So, oh yes.
Do you want us to turn in our makeup exam?
Ooh, yeah. Can you? Yeah. Let's do that now. Yeah. If you have the makeup assignment for the first exam, pass that up now. So I think I might be getting in trouble for giving you guys extra credit on this exam. So just know I'm taking one for the team. I guess the average was decent enough that I maybe wasn't supposed to do that, but oh well.
Isn't it your class?
You'd think, right? You'd think that. No. I mean, it seems reasonable. The average was in the mid-high 70s, so maybe I don't need to raise grades anymore. But
raise our hopes.
You guys will need it after that quiz that I just did. All right, so how would we find, say, this probability? So the scenario is this. We have some manufacturer of thermometers, and, well, we know that theoretically the freezing point of water is supposed to be 0 degrees Celsius, right? So this company manufactures thermometers, and some of their thermometers do read 0 at the freezing point of water. So you put water at a certain temperature and you notice that it starts to freeze, and then you look at the thermometer. So some of them do give you exactly 0. But some of them give you numbers that are spread apart from 0, right? The manufacturing process isn't perfect. So they make thermometers that are sometimes off from what they should be, what the true value should be. So this is a histogram that represents number of thermometers, and these are temperature ranges. So this is an example from your, they don't give a histogram, but your book gives this example, and I'm going to follow it because it's decent. So this says, for example, that if you if you selected, well, this says, say, given a sample of thermometers, 25 thermometers read between -4 degrees and 0 degrees as the freezing point of water. All right? And this says that, well, 5 thermometers were so bad that when water started to freeze, they read between 1.6 degrees and 2 degrees. So there are some thermometers in here that read, say, 1.7 degrees when water froze. So does everybody understand the setup of this histogram? All right, and just from what we know from, say, Chapter 3, this looks something like a normal distribution, right? Values are clumped more towards the center. So there are a lot of values that read really close to 0, and less values that read, say, far away from 0. So that's what we'd hope for, right? If we were manufacturing thermometers, we wouldn't want a lot of thermometers to be way out, measuring 3 degrees when it should be 0. So what if we wanted to find the probability that the thermometer reads between, say, -4 degrees Celsius and 0 degrees Celsius? So how might we find that probability? Say this is the whole population that we've recorded here. I don't know who was first. Leanne, right?
Yes.
Yeah,
I
we'll
just
go.
have a question. Does
Sure.
it matter that all those values don't equal to 100?
No. So
Doesn't matter.
just suppose that the company made, how many are here? 90?
Yeah.
So just suppose the company made 90, and this is what we're looking at for now. So we're going to change that in a bit, but for now it doesn't matter. So how would we find, so here's a question that'll help us get there. Is this a relative frequency histogram, a histogram, a percent frequency histogram? So is it relative frequency? What do we know about relative frequencies? Or frequencies? If this was a frequency histogram or relative frequency histogram, shouldn't these numbers be, say, less than 1, and they should all add to 1? So that should tell us that it's actually just a histogram. And if we made these relative frequencies, then that would probably tell us something like a probability, right? So what would the relative frequency of -0.4 to 0 be? Yeah, so it would be the number of thermometers that measure between -0.4 and 0 divided by the total number of thermometers. So that would be the relative frequency. So imagine if we had all of these thermometers in a bag and we just mixed them up and shook around the bag so that when we grabbed one out, it was a random process. So this is starting to sound like a probabilistic process, right? We have some thermometers in a bag and we can choose one. So what's the probability that we choose one and it measures between -4 and 0 as its temperature for the freezing point of water?
25 out of 90.
So that's it. So it's 25 out of 90. So that's the probability that a thermometer reads between -0.4 and 0. So last time, and remember before spring break, I asked you the question, what would be the probability that the thermometer, so I asked you it in a different context, but I'll ask you it again in this context. What is the probability that the thermometer reads exactly 0 degrees? 0, right? So we said that really, so there'll be some really accurate thermometers, but they'll never read exactly 0. They might read 0.00001. That would be really accurate, but it'll never be 0.0000 repeating on forever, right? That's impossible to do. So that'll be important to see. So how would we answer this question? So the thermometer reads less than 0 degrees Celsius. So how did you get that?
Well, the 25 plus the 20 and 10 on the left.
That's it. Nice job. So it would be 25, right? There are 25 thermometers that read between -0.4 and 0. There are 20 thermometers that read between -0.9 and -0.5, and 10 that read between -1.4 and -1.
Now, wouldn't you exclude the ones that measured 0 though, because this is less than 0? Because Because if it was 0.5, that's over 0.
So it doesn't matter. So if we included the ones that measured exactly 0 here, in here or here, it doesn't matter because none of them measured exactly 0. As weird as that sounds. 25, 35, 45, 55. So remember, one question was, what is the thermometer? Let's see. Thermometers read between a certain range. And the other question was, what's the probability that the thermometers are less than a certain point? So those are two important probability questions that we can ask. So we want to move from frequency distributions, so histograms like this, to what we're going to call normal random variables. Do I want to say anything about this before we go on? Does anybody have any questions about this before we go on? All right, then let's go on. So really what we're going to do when we talk about a normal distribution is we're going to imagine that instead of this company making 90 thermometers, we're going to imagine that they keep increasing the number of thermometers that they make until they make infinitely many thermometers. So we're going to imagine some population of an infinite number of thermometers. So there are just a ton. That's all you need to remember. And if this was a decent, so say we have a population of infinitely many thermometers, and this was a sample from it. If this was a good sample, what would the population look like?
The same?
It would look
Or similar?
the same except for what? What's that? Yeah, these numbers would be larger, right? So the number of thermometers that read in this range, it would have the same shape, but this would be higher, right? There would be a lot more thermometers here. So that's all that we're doing when we go from a histogram like this to a normal distribution. So I'll draw the normal distribution for you. And we're going to start with the standard normal. So the standard normal distribution, I'll tell you what standard means in just a minute. But so now we can think of, say, this is the temperature, and this axis as the number of thermometers. And so this would be, say, 0 degrees. This might be 1 degree. So this is, this would be what's called a normal distribution, right? We have some units on the x-axis, and we're measuring how often things at this unit occur on the y-axis. So some things to notice. Let's see. So where would the mean of this be? Where would the average be? So it would be at 0, right? So remember, for when we saw histograms, the highest value in a normal distribution represented its mean. So the highest value represents its mean. So what is the mean for these thermometers?
But they're accurate.
It means they're accurate, right? So remember, when we were talking about populations, we use the symbol mu as the mean, rather than x bar. X bar we reserve for samples from the mean. And we're going to suppose that the standard deviation for this sample is 1 degree. And so what does that mean the variance is? If the standard deviation is 1, what is the variance? So if the standard deviation, remember the standard deviation for a population, we denoted this symbol, which is sigma in Greek. And we'll say that this is 1 degree. So what is the variance? Yeah, so the variance, remember, is just sigma squared. And well, 1 squared is just 1. So this is a standard normal distribution. So what makes a standard normal distribution? So a standard normal distribution is a normal distribution. So remember, normal distribution means that it has this shape, right? Values are clumped towards the center. The mean is in the middle. So is the median and the mode. They're all the same thing. Values get less frequent as you go out towards the tails. So this is all what it means to be a normal distribution from chapter 3. So it's a standard normal distribution if mu is equal to 0, whatever your units are. It doesn't just have to be degrees, right? It could be anything, pounds, inches. And sigma squared is equal to 1. So wait, a standard normal distribution is a normal distribution if the mean is 0 and the variance is 1. Wait, that still doesn't seem right. I don't think I'm writing English.
Yeah, there could be other contexts of writing down these that would not be temperatures.
This should be
where the mu would be not 0, right?
Yeah, I was gonna say, I was like, because couldn't that just all be essentially shifted to the left, but all still be your standard bell curve?
Yes.
Where your mean is your center.
Is it sort of like a skew to the both sides graph?
So we're reserving the word standard to mean 0 mean and unit variance, 1 being the variance. So it's certainly true that we can have some other process where we have a normal distribution and the center of the normal distribution, the mean, is 5 feet 7 inches. That might be a normal distribution for heights, right? And the mean height might be 5'7", although that's probably high. So we could have a normal distribution with a different mean and a different variance, but that's not a standard normal. So a standard normal means 0 mean and 1 as the variance. So does that make sense? All right. So now, if we have the normal distribution like this, how are we going to go about calculating calculating probabilities like this? So it's going to be maybe more difficult. So that's what we're going to have to get to now. So let's try a simple one. So this one we should know by heart. So the thermometer equals 1 degree. So what's the probability that the thermometer reads 1 degree? If you say sampled it from this giant population and you want to know what the probability that you get one that reads exactly 1 degree when it's supposed to read 0. 0, right? So this probability is 0. So in general, for continuous random variables, we don't care about the equality, right? For discrete random variables, when this was, say, x equal to 1, when x was the number of heads in a coin toss, that we cared about. But here, we don't care about equality. We're going to care about inequalities. Yeah?
So the probability that it equals 1 is 0 because we don't know exact values?
Well, it's because the probability, so any thermometer equaling exactly 1 degree is impossible, because really the thermometer probably only goes out to 1 or 2 decimal places, and really after that 1 or 2 decimal places it probably reads something like 1.00035 or something like that, and we can't detect that 35. So it can't equal exactly 1. I know that seems weird, and to really understand it, you'd have to take a lot of math.
Well, it's
So you
just
just have to trust.
thermodynamics, isn't it? It's just the way temperature works. You can't really put a precise calculation on it.
Sure, because temperature is continuous, so
Yeah.
there are infinitely many values, and the probability of any one of them is 0.
Well, it's like my car gives me my gas mileage, my average of my gas mileage, how much fuel I'm using, and it's never consistent. It's always all over.
Yeah. All right, so we care more about things like this. So what is the probability that the thermometer reads, say, less than or equal to 0 degrees Celsius? So this is a probability that we care about and that we want to try to calculate. So how are we going to do this? Well, do you remember back to when we started talking about probabilities and we made an analogy between probability and area? Does anybody remember that? So we have these diagrams of like a set, and we said that if this is a set, the probability of this set is just like the area of this set. Nobody remembers this.
Are you trying to
two
say that the probability right there is 1/2 because literally half the thermometers are on that side of the...
So that's where we're going, yeah.
Oh.
So what I'm trying to, I was trying to draw an analogy between what we did earlier and what we're going to do now, but since nobody remembers what we did earlier, let's just do what we're going to do now. So probability, when we think about a normal distribution, is just going to mean the area under this curve. So it's going to mean this area. So let me erase these. So this area corresponds to probability that the thermometer reads less than or equal to 0 degrees Celsius. Right, this shaded area. So if I asked you to calculate the area of a box, say this is an x-axis, this is a y-axis, this is 0, this is 1, and this is 1. How would you calculate the area of this box? So area of a rectangle is just the length of this times the length of this, right? So the length of this is 1, length of this is 1, so the area is equal to 1. Because it's just a rectangle. So if I gave you a triangle and I wanted you to calculate the area, what would you do? Well, maybe you don't know it off the top of your head, but you'd have...
A squared plus b squared equals c squared.
So not quite, that's the Pythagorean theory.
Based on
1/2 base times height.
I think Lauren might have said it.
Based on height over 2.
Yeah, so you could find the base, you could find the height, and you divide by 2. So it'd be half of a rectangle. So these are nice geometric figures, and we have formulas to calculate the areas. So how would you calculate the area under this weird curve below here?
Graphic.
Well, we basically did graph it.
Well, you could just say it's half of the area.
So yeah, that's okay. So it is half of the area. What is this whole? What should this whole area equal?
1.
So it should equal 1. Why? When?
Right there on the bottom.
Where?
Standard deviation.
Oh, that's just the standard deviation. That means the standard deviation is 1. So this is 1 standard deviation from the mean. This is 2 standard deviations from the mean. But the total area should equal 1. Why? Somebody should be able to see this.
Oh,
It's your distribution chart has to add up
Yeah, I mean, it's basically the same thing, right? If you take the probability that that your thermometer is in this population, well, that probability is just 1, and that's just the probability that it's somewhere in here. So that's the area under the whole curve. So, Leon, right?
That's what I was going to say.
You were saying, well, the whole thing is 1, so this must be a half.
Yeah, 0 would be no probability. You know, so 0.5 would be that whatever.
Sure. So for any probability distribution, right, this is a normal probability distribution, the area under this curve should equal 1. And that's analogous to, remember the charts that we had for, say, binomial random variables or just other discrete random variables. The probabilities had to sum to 1, right? That was important. Probabilities need to sum to 1. Well, this is just like the probabilities summing to 1. The area under this curve has to equal 1. And we're interpreting areas as probabilities.
Now, because that never actually touches 0, does that matter?
No, so I mean, I guess that's kind of important. This just keeps going on basically forever.
And it gets closer and closer, but it never actually.
Yeah, so it gets closer and closer to 0 in this direction, closer and closer to 0 in this direction, but it never stops.
That's assuming we have an infinite number of thermometers.
Yeah.
Well, an infinite of degrees. You're going degrees.
Yeah. So sometimes, and this is a philosophically interesting point, sometimes these things break down in real examples. So this is like a theoretical construction almost. So don't think too hard, otherwise you'll be a philosopher. So if you wanted to calculate the area under this curve, you would have to do this. I'm sure you all know this. Right? Just do that integral, and you got it.
Wheat.
So how many people took calculus? So a few people, maybe a few people know what this means. But I bet you couldn't calculate it because it's a real pain in the ass. So how are we going to calculate areas when the formula is this complicated and we don't know calculus?
Plug it in there.
So you could use technology. So maybe your fancy TI-80, whatever it is, could help you. But what's even better is we're going to have a chart to use. So does everybody have worksheet 5? Maybe it is? So on worksheet 5, I gave you an important chart. So does anybody not have it? It's okay. You can raise your hand. We'll try to pair you up with somebody who does have it. Because it's good to look at it. So if you guys want to look on with somebody else, I don't think I have anything on. But I will put it on the projector.
It's on the back.
Yeah. So basically, what this chart is.
We get this on a test.
Yes, you will get it on a test. So the chart is this formula worked out for a whole bunch of numbers. So somebody who is a real loser, right, worked out this quantity or estimated this quantity a lot so that you and I don't have to do it every time we need to. And remember, the area.
He just plugged it into Excel.
Yeah, I mean, actually, they did this. People made these charts before computers, so they actually did some, like nasty pencil work.
Yikes.
And then they double checked it in Excel.
Hope they got paid well.
So do I. So don't, unless this looks pretty to you, don't write this down because we're not going to need it. I should have never showed it to you. I should have told you to wait and take calculus.
Like, it's pretty.
So let's try to make life a little bit easier. When I say thermometer reads, let's just call this X. All right, just like we called, say, the number of heads in 4 flips of a coin, X. So this is going to say X is equal to the temperature the thermometer reads. All right. right? And of course, x could equal something else, right? X could be heights of people at Red Rocks, heights of people at Red Rocks Community College, right? We can think of that as being normally distributed. A lot of people are 5'5", 5'6". Less people are really tall, and less people are really short. So these are two examples of normally distributed random variables. So let x be a standard normal random variable. So that means, what does that mean? That x is just like this height random variable, right? It has, so I'll write it down. Yeah, x has mean equal to 0 and variance equal to 1. So that's what it means to be a standard normal random variable. And in addition has this shape, right? This bell shape. So the probability that x is less than or equal to, usually what's written is this, but I think you guys are going to get mad at this. So this says the capital X is the random variable that's distributed normally. And this little x is some value, just like we put 0 here. So the thermometer reads less than or equal to 0 degrees Celsius. That's the little x. We could have put, what, 2, right? Then we'd want to calculate the area beyond this. So does the little x bother anybody? Should we call it something else? We're okay. I try to make it script so that it looks different than this one. But this reads the probability that the random variable capital X is less than or equal to a value little x. So that's really all it says. So the probability that the random variable x is less than or equal to some value little x.
And you would always tell us what the little x is going to be, right?
Yep, so I'll always give you an actual number here. So these probabilities are given by the chart on worksheet 5. So we should all look at that chart. I think maybe it'll be helpful if I try to bring it up here. Now I just have to figure out how to do that. So we're going to learn how to read this chart, and reading the chart is going to tell us how to calculate this probability, right? And that's going to tell us, what does it tell us in terms of a picture? It tells us the area under the curve less than the value of x. Right, so x's are along this axis right here. And when we fix a value x, the chart tells us the area to the left of that value, under the curve. And that tells us the probability that it's less than that value. Cool. Did that turn on?
So if we don't have a standard normal distribution, then we can't calculate this?
That's very important,
Unless we figured that out?
So if we don't have a standard normal random variable, then we can't use the chart yet. But we're going to learn how to use the chart when we don't have a standard normal soon. So I'll teach you how to use the chart, how to translate a non-standard into a standard. And it doesn't look like this is going to work. So I say we just look on with somebody next to us if you don't have one. And I need to look on with somebody too. So you guys can look on together. So notice that this value z up here in the corner, these are values of z. So z could be really far out this way, right, negative 3.9 is the first value on there. That would correspond to something like out here, right? Very far out in the tail. And then you keep getting bigger and bigger, right? So the value negative 2 would correspond to this here. So these values are areas to the left of the curve. So then does anybody know what the values across the top are?
The temperature?
So the values across the top are actually the next several digits in the number. So
so 3.900.
yeah, so the first value in the chart, if you read down the column, the first value is negative 3.9. And then if you're under the first column, you just have 2 extra zeros there. So you see this number 0.00005? That number corresponds to the area under the curve to the left of negative 3.900. So that would be a very small area, right? The curve is getting really small, and it's just this little area out this way. And it's equal to 0.00005. So how about, so where is 0 on here?
There isn't one.
Well, you can flip over, right? It keeps going. It's even worse than you think.
Oh.
So how would you find the area under the curve to the left of 0 on this chart? So can somebody find it for us?
All the zeros. 5.50000.
There you go. So it's if you go on the last page of the worksheet, it's the first row in the chart and the first column, right? 0.0 and then 00. So the top part of the chart is just adding numbers onto the end of a decimal number. So how could we find, say, the area to the left of 0.002?
That would
Yeah.
be
So let's make this an example. So area to the left of 0.002. So what would you do to find what?
Does it go to the thousands or the hundreds? Is it 0.02 or 0.002?
So it's adding on to. So let's
this is -0.
question.
Okay, so if we're looking like to the left of 0, what do we look under the -0.0?
Well, no, the negative would give you. So if you look at the bottom of the first page, negative 0.0. Well, it gives you the same value. Negative 0.0000 gives you the same value.
But
So
if
if you
move over one to the negative 001, it's 0.49, and if you go to the positive 0.001, is 0.50.
right, because the negative values, you're moving over this way a little bit,
Mhm.
so the area will be smaller. If you go to a positive value, you're moving over this way a little bit, and the area will be a little bit larger.
So which 0 do you pick though?
Well, if you want 0.00, it's the same.
Okay.
So the last value in the first column is the same as the first value in the first column on the next page. So I'll draw part of the chart up here to help you out a little bit.
It shows that like 3.9.09 is really close to 1, but not quite 1.
So this is a part of the chart, right? So this is your z value, and the first row is negative 3.9, and then I'm skipping 2 rows, and I'm just going to go over to 0.02, right? Just to make things a little more interesting. So what is this value? So this value is the probability that z, so z is a standard normal random variable, right? That's what this whole chart tells you. So I used X, the chart uses Z, maybe I'll use Z from now on. So this tells you that the probability that Z, a standard normal random variable, is less than negative 3.902 is equal to 0.00004. So this is how you read the chart. So what if we say 1.2 and we have 0.01. So what should the value, what is the value here for 0.01? Anybody?
8866.
So
0.11314.
Is it negative?
So this is positive.
That's positive.
Positive, yeah. So this should be 0.88686. So how do we write this in terms of a probability?
Same way.
Same way, right? Question?
No, I was just going to tell you.
Oh, yeah. So what do I do?
Probability that Z is less than or equal to 1.2. And then 0.01.
Yeah, remember we have to include this column, right? So this column says take 0.1 and add it on to the end here. So 0.1 is equal to what?
0.8867.
There we go. So I know this seems tedious and annoying. You have to read from this ugly chart.
So
But remember, it's a lot easier than calculating that integral, that nasty math function. Lauren?
So is there like another chart? Because we're missing the hundredth place. And for this chart, it's all going to be 0.
For
See how you 3.902? We only have 0, 1, 0, 2. We don't have 1, 1, 1, 2, 1, 3.
So you should have a lot of values out to the thousandths place, right? This should be
Just hundreds, right?
so this gives you the tenths place, this is the hundredths, and this is the thousandths, right?
I mean, technically, if you're reading this just on here, it's just the 0 is the tenths place, and the 2 is the hundredth place, or the 1 is the hundredth
Yeah,
place.
it's confusing.
It should just be 3.92 is what I'm thinking.
So it should give you out to 3 decimal places.
Yeah, it does.
Well, but it technically, if you go 0.0 and then you look up top, you put another 0.01, there shouldn't be a point in front of that.
Yeah, I guess there probably shouldn't be. I didn't make this chart.
Well,
That-
there should be
because it
because
looks
it's trying
like
to
a
tell you to
decimal.
add a 0.01 instead of a full.
Yeah, so really it's telling you to add that on. So you're taking what's in this column over here and adding it to this column over here. So that should give you, so negative 3.9 plus this, well it's really minus that, gives you this.
So then we don't have anything that's past 0.1 from the hundredth place.
That's right. So the area, if we moved over very slightly over this way, we'd get a little bit higher area, but we can't expect the mathematicians who made this chart to calculate every single value, because they'd still be doing it right now. Right? There are infinitely many values. They can keep calculating way out to the trillionths place or whatever. So we're going to have to approximate sometimes. And most of the time, approximations out to 3 decimal places is really good. It's a really good approximation. So we'll just have to deal with their approximations.
It's like our clock right now, like our calendar. There's not that many decimal places or something like that.
Sure.
So we don't care at all about the right, ever?
Meaning calculating the area, say, out this way?
Yeah.
Yes, we do. So how are we going to do that?
Flip it.
So did we answer questions that we wanted to answer? So what was this right here? This probability. So same example as before, we had a thermometer and it reads, so this is like our X. Thermometer reads a certain temperature. Thermometer reads less than 0 degrees Celsius. So look up on your chart, what is that? Or reset it, so if you don't want to look it up again.
0.5.
Yeah, so we can just say 0.5. The chart gives a few zeros afterwards. And let's do,
Now, again, how do you know which 0 to choose?
so they'll both be the same. So if you look at the bottom of the chart, very bottom, negative 0.0, and in the first column, it
The
says
first
0,
column
0.
will be the same, but if you go to the right, they differ.
Well, that's because then you'd be going over to
Yeah,
negative
way or
0.001. And that's different than
one's
0.
going up and the other one's going down.
So what is this question here? So area to the left of 0.002 is the same thing as the probability that z is less than or equal to 0.002. And what is this value? We read this off the chart, right? What is it? 0.50798. So how did we calculate this? Well, we have the chart here, and we should have 0.0, and then up here we should have 0.01 and 0.02. And the value that's 0.002, whatever's here, will be your answer. So it should be this. I probably should check you. All right, so does this make sense to everyone? So the chart calls it Z, so maybe we should call it Z. It doesn't matter, right? It's just a label. But sometimes standard normals are called Z's. So this would be Z too. So you don't have to change this if you don't want to. I'm just trying to relate this to the chart. So the probability that a standard normal random variable, Z, is less than or equal to some value is given by the chart in the way that we just calculated, right? In the way that I showed you to read this chart on a few different ways. So we're going to do some more complicated questions in a minute. But before we do that, does anybody have questions? People look like this is crap. No? All right, good. All right, so let's try a slightly more difficult question. So what if we wanted the probability that Z is greater than 1? So how would we calculate this? I don't want to add too much. I think that would take too long. So there's a trick. How could we represent this on as a picture? So a picture like we have over there. So this we represented in the picture as the area to the left of 0.002. So very close to 0. We'd go up and it would be this area here. Right? That's all this says. The area to the left of this, when we have a normal distribution, standard normal, is this. And that makes sense, right? If the area to the left of 0 is 0.5, well, the area left to just above 0 should just be just a little bit above 0.5, and it is.
So you would go over 1 and then everything less than 1.
So is that right? Is this area equal to...
No, it's greater than. So it'd be to the right.
So if this was 0, right, standard normal, this would be 1, 2, 3.
Right.
Is it just this area down here?
No, it's
No,
that
where-
area that way.
So it's this area this way, right?
Right.
So we want to know, how do we calculate this area?
Would you do 1 minus the value?
Yeah, so how did you get that? So you're thinking. So why is this area 1 minus this area? So it's equal to, remember, probability we can just think of as area. So the area to the right of this value is equal to 1 minus the area over here. So maybe let's think about our box again. So think about areas. This is 1, this is 1. Well, I'll make this 2 because that doesn't look like 1. So if this is height 2 and width 1, what is the area here?
2.
Area is equal to 2. So what if I said, I don't want to make it too annoying. So what if this was 1? So what is this area here?
1.
This is 1. So area equal to 1. What is this area here? 1. So we can think of this area here as the total area, 2, minus the area that you're leaving out here. So this is 1, this is 2. So the total area is 2, subtract 1 and you get this area. So that's all that we're doing here, right? We have a total area which is equal to what? 1. So that's where, oh geez, I forgot the 1 minus. So the whole area is 1. And if we subtract 1 minus this whole area, we should just get this area. So that's all that this says. So we're subtracting off what we can get from the chart, and that will give us this area. So really, these mathematicians who made this chart, they could have made another chart, and they would evaluate some other ugly mathematical expression that would give you this area here. But they were smart, and they said, I don't want to make 2 disgusting charts, I just want to make 1. So how do I make 1? Well, I know that the area of this whole thing is 1. So I take 1 minus this area and gives me this area. So how would we find this? So how do we get this? Chart, right? So what does the chart say it should be? That's right. So in order to find this right here, you'll look at your chart and you'll see Z, and on the left side you'll see 1.0, and then you'll see 0.00, and then the number that corresponds to this row and this column is going to be this right here. So it will be 0.84134. So then this quantity here, which by some fancy area reasoning we said was 1 minus this probability we get from the chart. So this is all equal to 1 minus 0.84134. And what is that equal to?
You need a calculator for that.
Sure. Maybe. So it should be, well, I'll just approximate this by 1.84. That makes it easier, doesn't it? Now what is it? 1.6. 0.16.
Well, it should be, if you look on the opposite of the chart, it would be the 0.15866.
So
you look at the negative one.
How did
right?
you get that?
Go to the negative one on the opposite side of the chart.
So you went here, and you're saying, look, this area is equal to this area, if I drew it right. So what does that tell you about a normal distribution? It's symmetric, right? It's symmetric around the y-axis, the 0 point, the mean. So what does that tell you? That the probability that z is greater than 0
Equals to the probability
is equal to the probability that it's less than 0. So this area, if I drew it right, should be equal to this area. And that means that this area, when I cut it off here, is equal to this area out here. So really there's 2 ways that you can do it because normal distributions are symmetric. So that's right. So we have a few minutes. I do want to get to non-standard normal distributions today, but I think what we should do is we should be able to do problem 1 on the worksheet. So I want to make sure that people are understanding this. So why don't we work on problem 1 by ourselves or with the person next to you for a little while, and let me come around and explain things to people if they're having trouble. So this doesn't mean leave. This means, you know,
This person's
actually
not
do
being
this.
leave.
So I will, I'll come around and make sure you can do this, and then we'll go back and do other normal distributions. Sorry.
Because 1.906 is different than 1.9.
Yep.
I would round.
No, 1.961 round up to 9.
So
We
you can
can
find,
get 1.906. That's different from 1.96.
let's see here.
So this one can be 1.900. That's not 06, and neither is 01.
This should be 1.96.
Well, right here it just says 1.96.
Yeah, no, that's what it should be. Did I tell you something wrong?
Well, no, but it's just when you look over here, there's a 1.906.
No, this should be, so I think I did something wrong. This should be 1.966.
Oh, it should be the same?
I think
Okay.
So
So
it is
that
this
is the number we're looking for.
Yeah, this should be,
It is the 97500.
so it doesn't go out to 3 decimal places. It only goes out to 2. So this should be, instead of 0.6, it should be 6. Were you trying to tell me this before?
Yes.
You were, weren't you? Damn it. So this was, I forgot, what was here? 2 maybe?
So really you could ignore the other 0 at the top, right?
Yeah, so
Okay.
this number right here is the same as 0.02.
Okay. Okay.
So it doesn't go out to 3 decimal places, it goes out to 2 decimal places.
Okay.
I'm still on spring break. Sorry.
Me too.
That works for me.
So does that make sense to everybody? That's an important correction.
Yep. I've got a question.
Yeah?
What's this?
So that just means it's a standard normal variable. So this says Z is mean 0 to 2. I'll write that too.
Because when it's greater than the Z, that's when Right, exactly. So you just gotta remember to do the opposite.
Right.
Exciting.
Less than Z.
0 is less than or equal to Z. Z is less than.
And so if you notice that the directions of this question, I was being lazy, so I use symbols instead of words. So this says Z is a normal random variable, so N stands for normal, with 0 mean. So this spot always means the mean, and this means the variance. So that's what it says in English. So sorry for being lazy.
For 0 to 2, so we're looking for 2 is greater than 0.
So how are we going to figure that one?
Less
You
than.
find this and then subtract 0.
Less than
The space between like 0.
So you do want to find the
Wait,
slice, right?
no, but it's greater than.
Or less than or equal to 2.
So what's the number? 0 and 2. Let me just draw another one.
So 2 is bigger than Z, but
Right.
Z is bigger than 0.
Right.
So 0
Oh,
and 2.
so it is that.
Started, I
Right.
think maybe sometimes it's that.
So what do you do if you want to calculate this area here? Well, could you calculate this whole area? Right, that would just be probability that's less than 2 minus this one. So that's the way to do
But
it.
what about the 2 and to the right? So wouldn't you have to figure out the 2 to the right and the 0 to the left?
So if you just want this here,
Oh yeah, I guess.
you can calculate the whole area, including all this stuff,
Gotcha.
right, and then subtract off all this stuff.
Got it.
How you guys doing over here?
So you're saying from 2 to the left. So one of those. You were just negative.
Yeah. So this says what's the probability that it's between 0 and 2, which is the same as the area between 0 and 2 on that chart. So forget about the 0. Could you just calculate the probability that the area and the curve less than 2? So
Minus
how would you do that?
Well, it's just 0.5000.
So if you wanted to calculate
I got this.
just the area to the left of 2, so that would be the same as
0.
probability Z is less than or equal to 2, right? Area this way. This you just read off the chart, right?
Right.
So this area is this whole area minus this area. So it would be minus probability of Z less than or equal to 0. So that should give you the just this area.
So we need to because it's easier to look at it that way.
I know.
Because we're taking the back number and subtracting the
Well, no, so this chart just gives you the probability that it's less than when you're here. So this value is the area
So it's the
less than
0.9.
0.00. Yeah, so you do. So if you want to know the probability that C is less than or equal to 0, you find 0 on the chart.
Oh, just that one.
And what column corresponds to?
Because they correspond to all of these.
Well, so this value right here, this last value,
0, 2, 0, 1.
corresponds to the area of the
Oh, okay. So you
I thought that's
this is one number. Okay. So guys, can we figure out because I was thinking place technically okay, sorry. Yeah.
So if I had, say, Z less than or equal to 0.07 here, then
It would be 0 for this one. Okay. And is there this one would be just the one number? Because if it's less than or equal to, because up there we have a bunch of numbers. Write that out.
so if it's in between, so that's this one.
Yeah.
In between, that's the area under the curve in between 0 and 2, so the lines that are there. And how would you find out when you can calculate the area less than 2? How would you do that? So that would be the probability that C is less than or equal to 2. How would you find that?
Well, it always equals 1 and 0.
So wouldn't it be Z? Wouldn't it be 1 minus?
Exactly. So if you that
And then
number,
you subtract it from
Like,
Yes, because the area in between there is the area
But you
from
want everything
2 and
above
below
negative
everything. So
0.5.
all of that below 2
And
minus
you
the
could just
area.
find it, you could just subtract.
Yep. Yeah, so you correct it.
I know, because I had it was like negative
I'm not
3.
even
I'm like, oh, wait a minute, you want everything above.
So this is just another way of writing.
I have no idea.
So no, actually we have to do that. So let's do that.
I'm in the direction.
Okay, cool. So, we're
All right. So hopefully everybody's able to do the first 4 parts of question 1, right? A through D. So let's look at the last one, part E.
Can we look at C too?
Yeah, let me do E first, and then I'll get to that one. So, let's see. So let's remind ourselves, what is a z-score? So this question asks you for a z-score. What's a z-score?
Isn't it 2 standard deviations? Or
Minus
so you guys are all close, really close.
Divided
Divided
by
by
the standard deviation.
So remember how the z-score is interpreted. The z-score is just the number of standard deviations you are away from the mean,
Right.
right? So how many standard deviations is 1 away from the mean?
Right.
So the z-score would be 1.
1.
Yeah, so this is just a z-score. If we're in the standard normal distribution where the mean is 0, then when we go over 1, we've gone over 1 standard deviation, right?
Right.
Standard deviation is just 1. So this is 1 standard deviation from the mean. So this is just a z-score. Isn't that nice?
Right.
So this is 2 standard deviations from the mean,
Right.
or the z-score of 2.
Right.
And so this is -1, -2 z-scores. So if we wanted to know what's the z-score that corresponds to splitting the population from 80 below and 20 above, that's what E says, right?
Yeah.
So that would be the z-score corresponding to this area
Be 80.
of 0.8, right? So what is the value that you look to on your chart to find an area
Everything
less than
2.
that's 0.8? So how would you do that? How would you use your chart to find the z-score that corresponds to the area
It's D.
of 80? What's that?
It's D.
D?
Should be answer D.
0.84.
I went from 0 to 2.
I think, so you want to find, so now you want to look for something like 0.8 in the body of the chart,
Right.
and then locate that, and then look to the left, and that will give, the number on the edge will give you, so if you're, so you should have 0.8, and there might be some other stuff, we might have to approximate, right? But then if you trace back,
0, 2, 3, 4. I think was the
Z will, of course, there'll be some value here and some value here, and the number will be this with this added on as the second decimal digit. Second out there.
0.85.
I would say
Your closest is
0.84.
well, your closest here is 0.80234.
So the closest number to 0.8 is what?
Above it, yes. You don't want to be below, or just round it.
There should be one that's pretty close to it, I think.
Then it would be the one below. It would be 0.799955.
I would use that one.
Okay.
Whichever one's closer, I would use. So what
Okay.
values does 7.79999?
0.84.
So what's over here?
0.8.
0.84.
And then 0.4, 4, yeah.
So this, from this chart, we see that the z-score to area 80.8 is about 0.84. So that means to get 80% of the population less than you, you have to go over 0.84. So it would be, you know, somewhere right around
Where are
here.
you getting that number of 0.84?
Right here. 0.8. And then 4.
why
we're
0.84? Why not
skipping.
just 0.8?
Because
Because
You
point
need the closest value
yeah, you want
in
the
this
closest.
chart
We're
to
looking for
0.8.
we're looking for
And
the
this
first
is
value.
closer
in the
than
middle.
this one, yeah.
so it's a little confusing because the area under the curve is
Kinda go
close to
backwards.
the z-score. So let's do another one. What is the z-score?
To the 20%.
The z-score corresponding to, say, well, this you should be able to answer without the chart. The z-score corresponding to area 0.5 is what?
Zero.
Zero, right? Because 0.5 is half of the population below, and we know that that's zero. Half the population is below. It's a mean. It's a standard norm. So what if we made this, say, 0.98? What is the z-score corresponding to 98% below? So we want 98% of the
2.6.
population this way.
Yeah.
So what is it?
2.06.
0.05. What's the? So we probably have to approximate it out.
I know.
0.05. So
0.05.
0.98. So we want. Oh yeah, you are right.
2.05 is closer. It's 18 from versus 30.
There we go. So you could either put 2.06 or 2.05. Either one of those is okay. So it has to be an approximation. So does everybody see how we read this chart backwards? If we want to find a z-score, then we look for the area, the probability in the chart, and then read the numbers off of it on the outside. Cool. All right, so can I see? I wonder if we can do on the worksheet. Can I borrow this? So you should probably be able to do number 2, and problem 3 we're going to get to next time.
And we have a quiz next time.
Yeah, so we have a quiz next time, and it won't cover this stuff. That'll be next week. It'll cover binomial random variables, which is what we did before spring break. So the binomial formula.
What homework assignments could because I kind of missed the week before spring break because I had the flu, and I just need to know what homework assignments we had.
Sure. So the questions on the quiz will be from the worksheet number 4. So worksheet number 4 covered discrete random variables and a lot of binomial random variables. So it'll be from there. Yeah. So that's on D2L, and I don't know if people noticed, but I posted extra practice for binomial random variables. So I called it worksheet 4.1.
Yeah.
And that's more practice with that stuff because people requested it. So it'll cover that stuff. It'll be a question from that worksheet. Or 2, right? So if you have trouble, email me, come see me before class next time.
Make it happen.
So, should we know that formulas? Like, we should know what X is and like the N and the P, right? How that formula is set up.
Yeah.
Plug it in.
Yeah. Maybe I'll be nice and give it to you, but I might not.
Make sure.
Alright, see you later, Alex. Have a good one, man. Yep.
Which you want the council
Because it's the one we're talking about.
have petitions that you're.
Does everything record all right?
Huh?
Did you?
Yeah, it did. I think so.
You get famous